Good morning, algebra students. Today is our last day of review of exponential functions, and we're going to talk about growth and interest growth problems, specifically interest, decay, and geometric sequences. So we talked a little bit about this yesterday, but just want to go back and do a quick review of the different types of exponential functions we might see. So we've got the basic function, which is our beginning value of a, our growth factor of b. So in this case, it's expressed as a factor, so that means times 2, times 3, times 4. I'm just multiplying by some factor each time. That's our basic exponential function, and everything else is based on that. So after that, we've got the growth function, which again starts with, sorry, I'm trying to be fancy with pens here. It starts with the same beginning value, but then it grows by a percentage instead of a factor. We usually express that as a rate. So we add that growth rate onto 1. The 1 represents the 100% of the A, and then we're adding on whatever the growth percentage is. So the difference here is that we're looking at some type of a percentage growth rate. So that's where that's different than the factor. But other than that, it's really the same equation. They're both raised to the x power, x representing the number of times that we've multiplied the original amount times itself. We also have exponential decay. So exponential decay just means that we're subtracting a percentage instead of adding a percentage. So again, it's that factor is expressed as a percentage rate. Then today what we're going to spend most of our time on is the geometric sequences. So geometric sequences are really the same thing, except that we're using different symbols and we're not starting at 1, or we're not starting at 0. So we use n minus 1 instead of just n. So again, we're going to start with the same thing. This a sub 1 represents the first term, so that's the same on all of them. So that's my beginning value, or the first term. What's different with the geometric sequence is that I'm multiplying it times some rate, and this is actually referred to with geometric sequences as a common ratio, when we'll dig into that a little bit more too. But I'm raising it to the n minus 1 power, and we're using n minus 1 because we're starting at the first term and not at 0. So I don't know if this is going to be helpful or more confusing, but my equation again is going to start with a sub 1. I'm multiplying it by the common ratio. Think for a minute about the first term. So if n equals 1, I've got 1 minus 1, which is going to be 0. And whatever the common ratio is to the 0 power, anything to the 0 power is going to be 1. So this kind of proves why I'm using n minus 1, because I really want my first term to be my beginning value. So I don't know if that was helpful or not. That's why we use n minus 1 instead of just n. So now let's look at a couple problems related to growth. So we talked a little bit about growth yesterday, but probably the most common real-world situation where you have growth has to do with interest. Either interest that you're paying because you've borrowed money, or interest that you're earning because you've put money in the bank. So the very basic situation is when I put money into a bank account, I earn some interest rate, and usually it's almost always expressed as an annual interest rate. So if you ever are looking at advertisements for credit cards or mortgages, you're going to see this term APR, which stands for annual percentage rate. So there's actually federal rules that require lenders and banks to express it as an annual rate. So that's pretty typical. Where we get some variation is how often the interest rate is compounded. So how often are they adding interest into your account? So the most simple examples are that it's compounded yearly. This is the most simple example, but it's also like the least likely to happen in the real world. But in that situation, we're going to start with the initial amount. So our initial amount is always what we start with in our formula. And then we are adding on the percentage rate. So that's the 0.03. And we're raising it to we use T for time, but that's the how long we're putting it in the account for. So if I left my money in the account for 5 years, T would equal 5, and I would raise 1.03 to the 5th power before I multiplied it times 200. So again, that's the most straightforward example, but it's the least likely to happen. What is more common is that we get some kind of compounding semi-annually, or maybe compounding monthly, or maybe even compounding daily. So we have to make our formula a little bit more complicated. So again, we always start with the beginning amount, which I'm just going to highlight right now. This is the amount that we're putting in the bank each time, or again, it could be that we're borrowing. The formula is pretty much the same, except we change it a little bit to account for the fact that it's being compounded more often than once a year. So I still have my rate, but in this case, semi-annually means twice a year. So I'm going to take that rate and I'm going to divide it by 2 to give me the rate for 6 months. But then when I raise it to the power, I have to raise it to 2 times the number of years. So T is always the number of years. So notice that this is a different color. Notice that this and this are the same number. So I'm dividing it into 2 compounding periods. I'm going to multiply T times 2 as well. On the next one, if I'm depositing $400 and it's earning 2% interest, again, my interest rate is right here. And then I'm dividing it by 12 because it's compounding monthly. So that's I'm getting too fancy with the pens and I'm forgetting which colors I'm using. That's the 12. So I'm dividing it into 12 periods. So I'm creating a monthly interest rate, but then I'm multiplying it times 3/4 times T, and it's 3/4 because T is the number of years. So if I'm compounding every 9 months, I need to multiply 1 times 3/4 to get 9 months out of 12. So that's why that number is different than this number. So those are just some examples having to do with interest. But again, it's the same basic formula. And I'm going to just square this up here. It's the same basic formula where I'm starting with the beginning value and I'm multiplying that times some rate and raising it to whatever power, in this case, how many years of interest I'm earning. Now we're just going to do one example of exponential decay because basically it's the same as growth, but the rate is subtracted from 1 instead of being added to 1. So in this situation, a city currently has 5,040 students in its elementary schools. So that's going to be my beginning value. So y equals 5,040. I'm multiplying it times 1, which is multiplying by itself, saying that's where I'm starting. But it's decreasing by 2%. So I have to change that 2% into a decimal. So I change it into 0.02. And it's decreasing annually for the next 20 years. So I'm going to be looking at this over with an exponent of 20. So this factor becomes 0.98, and that's my decay factor. And because it's less than 1, I know that it is getting smaller versus getting bigger. And so that would be my equation that I would then pop into my calculator and find that the number of students in 20 years is 3,365 students. The last part of today's lesson is about geometric sequences, but I'm actually going to stop this video and start the geometric sequences in another video because I know some of you really only need to study the geometric sequences in a little bit more depth. So I'm going to stop this one and go look for the next one on geometric sequences.